Hello everybody. This video is brought to you by Asha Akanksha Foundation. My name is Siddharth, and in this video, I will be teaching about Master's Theorem or Master's Method. First, I will be explaining what it is actually, and then I will be deducing the Master's Theorem formula. There is a formula involved in the Master's Theorem, and I will be deducing that formula mathematically, and that's all that will be covered in this video. So first of all, whenever we are talking about algorithms, we most of the time we need to calculate the time complexity of the algorithms. Why? Why do we need to calculate the time complexities? Well, in the most basic of sense, the time complexity is one of the many factors which helps us in comparing the algorithms and telling which one is more efficient or which one is a better algorithm. We are, when provided many algorithms are doing the same thing. So we have to calculate time complexity in many scenarios. So how do we calculate the time complexity? There are many methods to calculate time complexity after seeing an algorithm, and Master's theorem or Master's method is one such method which helps us to directly deduce the time complexity of an algorithm of any given algorithm by following a certain formula. It is it can be said to be a black box which takes an algorithm and gives us its time complexity. It is usually used and it is mainly used for calculating the time complexities which involves recursions or the divide and conquer rules. In those cases only we use the Master's theorem or Master's method. Like in this case, it is written, it is a black box method to solve the many common recurrences in the algorithm design, especially divide and conquer. Whenever we are solving any problem using divide and conquer rule, which automatically becomes using recursions, then in those cases, we can just simply use Master's theorem, Master's method to get the time complexity. In the most basic of sense, the Master's theorem is a formula, is a function in which we can put values of certain variables and get the time complexity. So I will be introducing the formula for the Master's theorem now. Yes, there are several assumptions made while using the Master's theorem. You have to keep those assumptions in mind, otherwise your answer might come out to be wrong. First of all, like I stated in earlier videos that you should know what is a recursion and how we actually divide problems in recursion. So in a basic recursive call, we all know that there is. So in a basic recursive call, we all know that we are dividing a big problem into several small problems and then solving the small problems using the same algorithm that was being used to break down and solve the big problem itself. So we are given a certain sized big problem. We are dividing it into smaller chunks. Now in now one assumption that we follow in Master's theorem is that all the chunks, all the sub problems will have equal size. Yeah, this is the only assumption that we are following. I will explain it using a diagram. Like, suppose that we are given a main problem which is operating on a certain value of n. Suppose this is n, and we are using recursion to divide it into smaller subproblems. Suppose three subproblems. So these are suppose the three subproblems that we are dividing it into. So by our assumption, all of the three subproblems should have equal size, and hence all of the three subproblems, they should be divided. The function call should contain the size of the subproblem to be n by 3 for all of them. And this is basically the assumption that we are following. We are dividing it into such a way that uh, all of the subproblems have equal size. This is the recursion. This is the Master's theorem formula. In this, Tn is the time complexity of the given algorithm. N is basically a function which will give us the time complexity of this particular algorithm. Again, I'm telling you that you should know asymptotic analysis and basics of coding to understand what this is. Tn is a function that will give us the time complexity of the given algorithm. N is the size of the input on which the time complexity depends, and Tn maps that particular size to a corresponding asymptotic time complexity, which is written in big O notations, big omega notations, and big theta notations, all that. So Tn is equal to A T n by b plus c into n to the power d. You must take care of all these constraints on the constants a, b, and d. C is a simple constant. It is a real number. It can be anything. And similarly, a, b, and d are also real numbers. A should be greater than equal to 1. Similarly for b, and d should be greater than equal to 0. Now, the a, b, and d are given some special names. A is called as the rate of spawning of recursive calls. B is called as the rate of shrinkage of subproblem sizes, and C is called as the it is the runtime of the uh, uh, combined part or the recursion. It is the it affects the runtime of the recursion. I will explain what this actually is. Now suppose I divide. This is a function call. Suppose suppose there was a function call f func n, and in that case this particular n, this is the nth level, first level, 0th level of the tree in which this particular function call is made, and this is the, and in that particular function call the problem is being divided into three subproblems, and the func n by 3 is being called three times. So you can actually see that in this problem, the main problem is being divided into three subproblems. That is, the main problem is being distributed into three parts. So we take the value of A is equal to the number of subproblems generated. In this case, the number of subproblems generated is 3, and we take it to be the value of A. A is the rate of spawning of recursive calls. It is called as the rate of spawning. Why? Because initially, suppose we are not, uh, suppose initially we were not given anything in, we do not know anything about this box and anything which is in it. We are just given a main problem. Now, when we say that the value of A is equal to 3, then that means that this particular main problem will spawn 3 more problems. All we need to know is that this one problem will spawn 3 more problems that needs to be solved, and that is called as the rate of spawning. What do we mean by spawning? Yeah, in this case, we can just take spawning to be generating. Um, in this context, I think the spawning essentially means generating. So one main problem generates three subproblems. So that's why A is called as the rate of spawning. Now B is called as the rate of shrinkage of subproblem sizes. That is, the main size of the subproblem is being reduced by a factor of 1 by 3. Uh, when we go down the tree of this particular recursive calls, then in each case the main problem size is being reduced by a factor of 3. So the value of B is 3 basically. It is just the amount by which, the factor by which the main problem size reduces in the further recursive calls down the tree. In this case, you see that n becomes n by 3, and hence we take B is equal to 3. And that's why we take B is equal to 3, because B comes in the denominator here. So that's why. And D is it basically affects the runtime of the combined part or the recursion. It is basically the amount of work being done in this particular main problem aside from the subproblems. Suppose that there is a certain amount of work being done in this main problem, which is W. Now this W will be divided into, suppose in each of the subproblems, the work done is equal to P. So this work is equal to 3 times P plus the amount of work being done in this particular main problem outside of these subproblems. That is, suppose that that work is equal to A. So the W is equal to 3P plus A. This is equal to W, where W is equal to where W is equal to the amount of work done in the main problem P is the amount of work done in each subproblem, and A is the amount of work done in the main problem outside of the subproblems. Intuitively you can think it as the amount of work that was please wait a minute. So intuitively you can think of it as the amount of work being done in suppose, first of all, suppose you don't know anything in this box. You were just given this main problem, so you want to tell how much amount of work is being done in this particular main problem. Suppose we take it to be W. Now, as we were solving our main problem using recursion, so that W was divided into 3 equal parts, and that was the work done in each of the subproblems. But apart from that, there is a certain remainder work remaining, which is being done in this particular main problem only, outside of these recursive calls, and that is the value of A, and that is this thing in the box. This is to represent that thing. So I think this formula is uh, is a very intuitive formula. I think you can easily look at it and find why the formula looks like this. Like Tn, you are given Tn. Now, as A is the rate of spawning, which means the main problem spawned A number of subproblems. So we take A into, now for each subproblem, the size reduced by a factor of B. So n by B. Now for each n by B size problem, we multiply it by A, or we can say that we add it A times, so that we can get the amount of work being done in the overall recursive part, and then we add just the amount of work being done outside of all the recursive calls. So I think this should be clear by now. And this is the main formula which is used to get the time complexity. The value of D, B, and A are the same. And you just have to, yeah, learn this formula by heart. That whenever you are given any divide and conquer type of problem, which uh, which follows a certain this form only, in which whenever you are given a divide and conquer type of problem, in which the size of each subproblem is equal to each other, then in that case you just have to compare it with the formula, get the values of A, B, and D, and then put it in this function. I will just briefly explain the function, briefly discuss the function. You calculate this value. We calculate this value. If it is equal to A, then it is order of this time complexity. If it is greater than A, then time complexity becomes this. And if it is less than A, then time complexity becomes this. So this was the main Master's theorem. Briefly saying that suppose you are given any recursion problem which is following the divide and conquer technique, in which each of the subproblem is of equal size, then you just have to guess the values of A, B, and D. A is the number of subproblems generated, B is the reduction in size, and D these things are calculated. These things comes out after using the recursion tree. So you create the recursion tree, you get a certain formula, you compare that formula with this particular formula, you get the values of A, B, and D, and hence you put those values in this formula, and then you get the time complexity. So, how do we get the formula? I think this is a very simple thing to get the formula, like the amount of work being done in this case. Suppose that the time complexity to do the work in this case is equal to Tn. I will just briefly explain the recursion tree. So yeah, this part is a dotted line, so which means there are certain more number of levels in this particular region. I have just skipped it and just gone directly to the leaves of the tree. And this is the first main thing. This in this this is the 0th level of the tree. This is the 0th level of the recursion calls. You Here the value of the input is n. Then I divide it into three subproblems, in which each of them the value becomes n by 3. The value becomes n by 3. And this is the leaf. And then these are the leaves, in which the size of the subproblems keeps on reducing until the value, until the time complexity just becomes a certain constant only. So suppose the time complexity, we have to find the time complexity of this particular problem. So we just calculate Tn. We have to find Tn. So Tn is equal to 3 Tn by 3. This thing is clear. Now I have to find the amount of work being done outside of the recursive calls. In this case, the amount of work being done is equal to n by 3 plus n by 3 plus n by 3 is equal to n. So in this case, in this particular level, the amount of work is equal to n. In first level also, the amount of work is being equal to n. Similarly, in all the subsequent levels, if you calculate it, then you find that the amount of work being done outside of the recursive calls is equal to n. If by that method you can get a certain general formula, like for like in this general case, the general formula. This is a simple example. In this case, the general formula is coming out to be this. So and hence I can take a is equal to 3, b is equal to 3, and d is equal to 1. I calculate b to the raised to the power d, which is equal to 3 to the raised to the power 1, which is equal to 3. Now I find that a is equal to b raised to the power d, which means that Tn, which means that Tn. Now if we compare it to the formula, a is equal to b raised to the power d, and hence Tn is equal to this, is equal to n raised to the power d, which is 1 order of n log n. And this is the time complexity of this recursive algorithm which is being created, which is being represented by this tree. Yeah, if for this video I will assume that you know what is a tree, and you know basic things like how a recursive function is actually represented by a tree. So if you know that, I think this will be very clear to you. If you don't know that, just pause the video and just yeah, so Google it. Yeah, I think you will get a one-page explanation. You can easily read it and find the answer. If you still have problem, then I will separately upload a video regarding that thing also. Now this is the formula, and now I will be going to the deduction of this formula. How did we arrive at this formula? So first of all, before deduction, there are several examples of algorithms of divide and conquer type algorithms which can be solved using Master Theorem. Whose time complexity can be calculated using Master Theorem. So these algorithms are merge sort algorithm, merge sort, yeah, basic sorting algorithm. I think you might know that if you know basic coding. If not, it doesn't matter. You can just look at it. This is binary search, multiplication algorithm that I discussed, Karatsuba. And yeah, Karatsuba, and this is the brute force, I think, multiplication algorithm. And this is the thing. Now I will be going towards the deduction of the function of the Master Theorem, proof of the Master Theorem. That is, how do we prove that this formula is actually correct? There are several assumptions involved while proving this theorem. First, we will take n is a power of b. That is, b is the shrinkage factor, right? And n is a power of that. So that in when we put it in this formula, this thing that comes inside the bracket, it becomes a simple integer and doesn't becomes a rational number like a fraction. It just becomes an integer, and only like that. And that's why we assume that n is a power of b. And then also, yeah, we, like I said, that in any recursion, in any recursive calls, we must specify a base case. So for the time complexity as well, we have to specify a base case. With different base cases, the time complexities can change. So we are specifying the time complexity for a one-sized problem to be equal to c. Now, what is the main technique that we are following here? It is just simply recursion trees. I would like you to know some basics about trees before coming at this video. If not, please, yeah, look at it right now. It will be very helpful in your understanding. So very general technique. It is a very general technique to solve recurrences. Many recurrences can be solved using recursion trees because each of the recursive problem, each of the divide and conquer problem can be visualized easily with the help of trees, and hence mathematical calculations can be applied easily. And yeah, when we are using recursion trees, as it is a very basic thing, so we can disregard that particular assumption. We can solve problems even without that assumption of the subproblems being of equal sizes. So yeah, like this was the recursion tree. I drew a similar recursion tree in the rough board. As you know that the trees has certain levels. This is level 0, level 1, level 2. At the level 0, which is the main function call of the overall algorithm, we are given the size of the problem to be n. Now that particular main problem spawns a number of subproblems, each of size n by b. B is the shrinkage factor, a is the spawning factor, and this process keeps on going on. It spawns another a, it spawns another a, and this keeps on going on. In each by after each level, the size keeps on reducing by b. In the level number 1, it was n by b. In the level number of 2, it became n by b square, and similarly it will keep on reducing until it becomes 1. Why 1? Because we took time complexity, we took base case for one size only, so it will keep on reducing until it becomes 1. So first of all, let us answer several questions regarding this tree. These are very simple logical questions. I think you will understand them very easily. So first of all, how many levels are there in the recursion tree? So we were answering that how many levels are there in the recursion tree. As it is a tree, so the number of levels is equal to the height of the tree. So let us just take the height of the tree is equal to h. Height of the tree is equal to h. Now in the diagram, like you can see that in the level number 0, the size of the main problem is n, or n can be said to be n divided by b raised to the power 0. In level 1, the size of problem is n by b, which is n by b raised to the power 1. Similarly, in level 2, n the size of problem is n by b square, and similarly in any level j, the size of the problem is n upon b raised to the power j. So after all this thing, the in the last level, the size, the level number will become n, the level number will become equal to h, that is j is equal to h after a certain in the last level, and the size of the problem is equal to n upon b raised to the power h, and that number is equal to 1 because that was the base case. Now we take, now this becomes n is equal to b raised to the power h. We take log on both sides. This becomes log n is equal to h log b. Yeah, I am assuming that you know these basic logarithmic functions, basic logarithmic calculations. If not, yeah, I will just briefly write the main formulas. So logarithmic formulas. So log AB. That these are some main things that I will be following in the video. So yeah, I will just write them here. Log B. So yeah, I have written all these formulae. These are some basic logarithmic formulae that will be used in this video. So I used this formula here. I used the third formula here in this particular step. Now for this, I added one more formula. So I applied log in on both sides. Then I take h is equal to log n by log b. Then I apply this formula, and then I get h is equal to log bn, and that is the number that is equal to h. H was the height of the tree, and height is roughly equal to the number of levels in the recursion tree. So that's why I have written this thing. Now, how many subproblems are there at any level j? Now, you saw in the main tree at the level 0 there is a simply one problem, that is a raised to the power 0. At level 1 there are a problems, that is a raised to the power 1. At level 2 there are in the level 1 each problem generates several other a problems, spawns a more problems, and hence the number of problems becomes a into a, that is a square. Hence for level 2 the number of problems are a square. Similarly, in this pattern I can say that for any level j the number of problems is a raised to the power j, where j is equal to 0 as the initial level was 0, and it goes from 0 to log bn, which is the last level. Now what is the subproblem size at any level j? Now you see that I already said that like at level 0 the size is n, which can be said to be n by b raised to power 0. Similarly for level 1 n by b raised to power 1, level 2 n by b square. Similarly for any level j n by b raised to power j, and that is this thing. Now what is the total work done outside of recursive calls? We know this formula. Now this formula is just a simple universal formula. Now in this case, the work done outside the recursive calls, I explained it that it is this particular part c into n raised to power d. So at any level j, the value of n becomes n by b raised to power j. The why? Because in the original formula, n originally represented the size of the problem. At any level j, the size of problem becomes n raised to n upon b raised to power j, and hence we can write the work done by its a problem is equal to this only. And at a certain level j, there are total a raised to power j subproblems, and hence we multiply it with this thing and we get this thing. And then work done at the leaf levels, it is equal to work done at each leaf into the number of leaves. Number of work done at each leaf is equal to c. Why? Because we took t1 is equal to c. Now the number of leaves is equal to a raised to the power log bn. Why do we take this thing? Why? Because we took a raised to the power j is the number of number of problems at any particular level j. So at the leaf level, j is equal to h is equal to log bn, and hence we take this thing. Mm, like j is equal to log bn. Then like we deduced in the original, in the previous slide, we deduced this formula. That is the total work done at any particular level j is equal to this, where j is the level. Now at the leaf level, at the leaf level, the j is equal to log bn. We substitute it in the original formula. We get this thing, and this is the amount of work done at the final leaf level. And we just have to see that this can be equated to this thing only. How this can be equated to this thing? I will just simply write it. So what we were given is that work done at the leaf level W is equal to C multiplied by A raised to power J, A raised to power log Bn, G Bn into raised to power D n upon B raised to power log Bn. This is the main thing that was given to us. Now we can take this is equal to C into, we just have to consider this particular part. This part remains the same. We just copy that. I'm just copying it as it is. Now for this part, for the remaining part, we take n raised to power d. We take d inside. Now for the denominator, we have b raised to the power log bn, and that raised to the power, in the denominator we had this. I have just yeah, introduced d inside the brackets. If I copy, if I just copy this particular part and write it separately, suppose that I write it here, then this can be written as n raised to the power log, then this can be written as n raised to the power log bv. I have used the fourth property here. It can be written as this, and entire raised to the power d, and then I can write it as simply this thing becomes 1, this thing becomes 1, so the entire problem becomes n raised to the power d. So this becomes n raised to power d, hence the denominator becomes n raised to the power d. Both of them cancels out, and hence this particular part cancels out, and hence only this particular part remains, and that is equal to this thing only. Now the total amount of work that is done in all the levels, if we add up all that work in the, then that particular thing is equal to this formula. How did we get this formula? Originally we had this formula. In that formula we take n raised to the power d outside, so we get c into n raised to power d. Then we just take everything related to j inside, so we take j inside, so therefore we get a upon b raised to power d raised to power j, as we were adding for all the levels. Hence we take j is equal to 0 to summation of j is equal to 0 to log bn. Now how to look at this intuitively? We know that a is the rate of spawning and b was the rate of shrinkage. Now the interesting thing is that when we take b raised to the power d, then it becomes the rate of shrinkage of work done. That is, if a certain amount of work W was being done at the current level, then at the next level, that work done for each problem becomes W upon B raised to power D. That is the RSH, that is the rate of shrinkage of work done. Now, how to look at it intuitively? Suppose that the rate of spawning, that is A, is equal to B raised to power D. That is rate of shrinkage of work done. That is the number of subproblems generated is equal to the amount of work that is being distributed to the each of the subproblem. Now, if we are given any certain given problem, then spawning new problems increases the amount of work done. But for each of those spawned subproblems, the individual work done reduces as well. Now, in this case, we are taking RSP is equal to RSH, which means that the increase cancels out the decrease, and hence the same amount of work done remains. The work done remains the same at each level, and hence we can just write that this A upon we can just write A upon B raised to power D. These both of these numerator and denominator are equal to each other. Hence this becomes 1. Hence this entire thing will become 1. Hence we can just say we are summing over 1 this number of times, and hence we can just take it to be 1 into log dn, which is this formula. Now, if the rate of spawning was greater than rate of shrinkage of the subproblem, which means after each level, as we go down the recursion tree, the amount of work done for each problem keeps on increasing, which means that at the leaves, there is the maximum amount of work being done. That is, the leaves dominate the runtime. If it is the opposite, then after each level going down the recursion tree, the amount of work done keeps on reducing, and hence the maximum amount of work done was at the root node of the tree, and hence work done at the root node is equal to this. Now I will just briefly go over the formal calculations. In the first case one I said RSP equal to RSH. RSP was A and RSH was V raised to power D. So we are taking this thing. In the original formula, this I take A is equal to B raised to power D. So this becomes 1. Now I am just adding 1 this number of times. So this just becomes 1 into log Bn, and hence this. This is basic maths. Now for the further formal calculations, I will just briefly go over the geometric summations. Suppose that we are given this geometric series, and we take the sum of the series is equal to S. Then if r is greater than equal to 1, then we take the sum is equal to this. If r is less than 1, then sum is equal to 1 upon 1 minus r, which can also be written as less than equal to this. So if a is less than b raised to power d, then this thing becomes this thing becomes less than 1, and hence if you originally see this summation series, it is a geometric series only, and in which r is less than 1, so we can apply this formula. Hence we can just say that we can keep this part the same, c into n raised to power d, but we can apply this 1 upon 1 minus a upon b raised to power d, where r is equal to b a upon b raised to power d, and we can apply greater than equal to because we use this thing. So this is a constant, c is a constant, we accommodate both of them into a new constant c1, and hence this things becomes c1. And if the a is greater than b raised to power d, then the original sum, this becomes greater than 1. We use this formula, and hence we just apply this formula as it is. And we can, and for the next step, we can just see this denominator is a constant, so we just accommodate into C2. Now we can just simply say that this numerator is always less than or equal to this thing. This is an intuitive thing. So this is written as this. Now we we take the power inside the brackets. So a raised to power log bn, and similarly this comes inside this. This is b raised to power d into log bn. D goes inside log, which is b raised to power log b n raised to power d. Now we apply the fourth property in the rough notes, that is this property, and hence we can just get n raised to power d outside. It cancels out with this. We get this thing. Now, what did these formal calculations give us? For RSP is equal to RSH, we got this summation is equal to this. Now, what was this summation? It was the total amount of work being done. So the total amount of work being done, it is dependent upon the time complexity, and hence we can just compare it with the formula in the given formula only. In the given formula, it was n raised to power log bn log n, which was we just cancel the c because we are taking big O notation. Similarly, we got c into c1 into n raised to power d for the a less than b raised to power d part, and hence this verifies this thing. And for this particular part, we got and for this part we got n raised to power d log bn, which which verifies that particular thing only. Tn is equal to big O notation of that. So for the a is greater than b raised to power d part, we get this particular thing, and it is just equal to what was given in the formula. In the calculation, it gives this, and yeah, you can just directly apply the property here, which I have given in the rough notes, and yeah, that is all. So that is all in this video. In the next video, I will be starting with the counting inversions. That is a part of the divide and conquer recursion problems. So thank you very much.